Search systems come with its own set of challenges. The data is often too large to be stored in a single node. We often need to handle 10,000 to 50,000 queries per second. Indices are very slow to build, but we still want to search the fresh data. So we have a bunch of different bottlenecks or trade offs: cost, latency, scale, freshness of data, high throughput. So, how can we solve? Milvus is the open source vector database that gives you the necessary levers to pick your trade offs and solve the bottlenecks you care about in your application. You want low cost, place more of your data in object storage. You want higher throughput, add GPU acceleration. You care about the fresh data, create a buffer that stores the new data and query from it, and use your main database for the older data and basically just combine the results. Today we are continuing with our series on search, and today on How AI is Built we are talking to Charles Xie, who is the founder and CEO of Zilliz, the company behind Milvus. Charles previously worked at Oracle as a founding engineer of the 12c cloud database, and we talk about the bottlenecks you will face in your vector database and how Milvus tries to solve them through multi-tier storage, GPU acceleration, and we also get a glimpse at the future, self-learning indices for vector databases. Let's do it.
I think a lot of organizations, from smaller startup to large enterprise, they are all looking for vector database solution, but their requirement is a little bit different. So for early stage startup, for smaller groups, they care about easy to use. So basically, they want to get the application up running with the least amount of time. But for enterprise, they care about performance, they care about scalability, they care about the maintenance of the system, how you easy to maintain at a large scale, and also security, compliance, and how you integrate with the ecosystem to take the data from the upstream.
And in terms of scale, can you tease a little bit what is like the largest vector database in terms of like dimensions plus amount of vectors you've scaled up today?
Yes, so for the largest one, they get like 100 billion scale. So basically, that's pretty much like the internet scale. So on the internet, we probably have like 1,000 billion, several thousand billion of vectors if you want to index the whole internet. So we saw some of the largest deployment in that range, and also we saw that there are a lot of companies, they are doing vector similarity search on a billion scale, 10 billion scale. And when it comes
Yeah.
to what we found is that like 3-4 years ago, they started with like 512 dimensions, and now they are in between 1,000 to 2,000 each dimensions, depends on the application they are building.
And what are the primary bottlenecks, in your opinion, when a vector database has to scale up to that size?
So the biggest challenge is that you have to build a scalable system from bottom up. I want to take one step back to give you an analogy. So if we look at the traditional relational database ecosystem, you will see that it was 20, 30 years ago, we have a PostgreSQL, we have a MySQL, and both of them are single instance, and so it's very easy to use. They get a lot of popularities. But when the data volume of the organization grows, people may need solutions that can accommodate a large volume of data. So that's why we have a big data. We have a lot of solutions to scale your database. And so in the very beginning, there comes a very easy idea that you add a sharding schema on the application layer. So there are a lot of solutions on top of MySQL, Postgres to basically partition the data into shards, and then you can do load balancing on top of it on the application layer. But this solution has some drawbacks. So first of all, is most of the solution is going to be like single write and a multiple reads. And then because you only get a single nodes or single instance for data modification, so it's going to be your bottleneck. And but if you want to remove that bottleneck, you have to build a system, you have to build an algorithm to support this distributed consistency. And it's going to be a lot of challenge on that. So we have this Raft proto implementation to support a distributed consistency. And also, when you are trying to build a scalable system, you add another layer of complexity in network, in communication, and which will further complicate the system. You have to consider that how you do load balancing, how you do data replica, how you do data failover and the data recovery, but all in a distributed environment. In the vector database space, and all this complexity also applies. And so we have to handle all this distributed data consistency. You have to, and what makes things more challenging is that vector data actually is very large. So if you look at a single entry of an embedding vector, actually is pretty much bigger than a typical entry in a traditional relational database system. As I mentioned, that a typical embedding vector, they could be 1,000 or even 2,000 dimensions. And so to transmit all this data over in a distributed environment, it could be challenging. And also, if you want to have this data consistency and also without sacrificing the performance, it's going to be a lot of challenge over there.
Yeah. And we moved a lot into the distributed system space already. So for those who aren't familiar with, especially all this data engineering stuff, Raft is basically an algorithm to reach consensus between different nodes. So if you have like a write, and I think it's easier to explain with like a transactional database, like if you have multiple transactional leaders distributed across the globe and you write like a new entry for a bank transaction that's happening into one of them, the other nodes have to be basically up to date with the node who has been written to, and you basically have to reach the consensus. And you also have to consider like the second part, basically the networking, that the network might fail or might take longer to basically communicate between the different nodes, which is like the additional complexity in distributed systems.
Yep.
Nice. And especially for Raft, can you go a little bit into the indexing part, especially because we don't really have the lightweight writes you typically see in transactional databases, but we have heavy vectors. So how are the heavy vectors basically distributed, and how does the consensus mechanism work exactly between the different nodes?
So basically, every vector database system may take a different approach, a slightly different approach, or totally a different approach to resolve this problem. But at Zilliz, the vector database system we build, so the open source Milvus, we can support different kinds of data consistency. So by default, it's going to be eventually consistency. But if you really want to have a strong consistency, you can also support that, but with a slightly loss of the performance. So it's going to be a little bit slower, but we do support different consistency level. And because we think that's important, a lot of companies that they're building vector database solutions for different scenario, and some of them care a lot about performance, and they want to real-time data visibility. And for those cases, eventually data consistency may be a good solution for that. And for some of them, for example, they're building this fraud detection, and also they are doing this real-time fraud detection for financial institutions, and they care a lot about stronger data consistency, and we can also support that.
Yeah. And you build on top of HNSW, the index. HNSW, especially at large scale, it takes a while to re-index when new vectors are inserted into the database. How do you actually support these like more real-time scenarios? So where you basically have a read in close proximity to a write.
Yeah. Yeah. So first of all, for all the data we ingest into the system, we have them to go through basically a distributed logging system. So at the moment, we are using either Kafka or Apache Pulsar for this purpose. And so every single data, we will put them into a distributed write-ahead log. And we're trying to use this distributed wall to support all these different kinds of data consistency. And other than that, as you mentioned, that for real-time data visibility and to make sure that the data are visible in real time or searchable in real time without a sacrifice of performance, we have two access paths for the data. So one is for this fresh data. So for fresh data, they first we put them into a buffer. But for the data in this buffer, we don't have to build an indexing algorithm. So basically, for the data in this buffer, we just do a brute force search and to make sure that the data is going to be accessible and searchable in real time. But when the data grows in this buffer, when it reach at a certain threshold, so once you reach at this threshold, it will trigger the index building and on the back end. And the Milvus system will start building the index. And it could be HSW, it could be this IVFPQ, and it could be other indexes behind the scene. So this is similar to strategy adapted by a lot of traditional big data or database systems like Cassandra also have this ASM tree structure. So they put data in the buffer and then they build this hierarchical merge tree and to gradually build or rebuild the indexes.
Yeah. And I think what we have seen, especially in the last year as well, with something like LanceDB, that a bunch of companies are starting to adopt a hybrid strategy of in-memory indices and disk-based indices. At Zilliz, is there something similar? And if yes, how do you actually decide which data goes into which index?
Yeah. So we were been doing this hybrid search for quite a while, since year 2019. But we take one step further. So it's not only about like memory versus local disk. We take one step further. So we have built this hierarchical storage. We have 4 layers of data storage. At the bottom, we can use all this object storage to store the data. And then on top of it, we can use local disk so for example, to use this NVMe disk to support the more efficient disk data access. And on top of it, we have a memory. And also for some user scenarios that we can even cache the data into your on-chip memory. So for example, it was 3 years ago, we started this collaboration with NVIDIA. So we are using GPU to accelerate vector similarity search. So if you are using a GPU, we can cache some amount of data in the GPU memory. So if you take a top-down perspective, you will see that so it's going to be GPU memory as a high-speed cache. Then you have the memory. Then you have a local disk, and then you have a distributed object store. So if you walk down into the hierarchy, you will see that you can put more and more data, but the latency may increase. Basically, you are doing a trade-off between the volume of data you can put in the system and versus the performance. If you want higher performance, you may want to build a system with more memory, with more high-speed local disk. But if you want to care about cost efficiency, you are building pretty much like an offline analysis application, and the performance doesn't matter too much. You can definitely use cheap machines that are with less memory, with less local disk, but with a larger object store. And so basically, we are giving our customer, our users, opportunity to configure their own vector database system in a way that they can make a trade-off between performance, consistency, accuracy, and also cost efficiency.
So it's really interesting. And when it comes to the GPU, are you doing GPU optimized indexes as well for the search? Or are you only using the GPU to basically do a faster or batch processing of the vectors?
The idea is using the computation power of GPU to accelerate the index building part, but as well as the search part. So for both parts, we have been working with NVIDIA to work on this GPU friendly or GPU customized indexing algorithm. So for example, there's an algorithm called Aura, which can support high performance indexing building and also indexing serving on this is also part of this new library released by NVIDIA called Q vector computing. And also you have to optimize the transmission between memory and the GPU because most likely it's going to be the bottleneck. The bandwidth between local memory to the GPU is going to be limited. So we have to implement a lot of algorithms to do data prefetching, data caching to minimize the data transmission between CPU and the GPU.
Yeah, and not even just if the indexes of the data can be stored in like multiple different tiers, not just the CPU and the GPU, but the different layers of storage as well.
Let me give you some more detail about it. So as I mentioned that the GPU is limited in its memory, but it get a lot of computation capacity. So that's why having this hierarchical data storage is going to be important. So basically, we probably cache or store most of the data in your local disk or in your object store. And we probably store like 1/10 of the data in local memory. And also on top of that, we probably 1 out of 100 in the GPU memory. You can accommodate the scalability of the data, support a massive amount of data, but also you can achieve super high performance because GPU only stores a very small percentage of the data. But you have to make a lot of modification of your indexing algorithm. Basically, it's going to be a hierarchical indexing algorithm. So on GPU, you just do some fast probe to find that, okay, for this particular search, which partition or which sector of data, which cluster of vector data, we should do the search. And also on the GPU, on the local memory, you cache more information and you can support more granularity. So the real vector search happens on the disk level. So you have this hierarchical indexing to make sure that you can make best use of a GPU, CPU, and the local disk.
At which scale of data have you actually noticed that the GPU brings a real performance benefit? So it will give like a benefit already at like small scales of data, but you will probably not see like a large impact in performance boost.
Yes, I would say it's not at which scale. It's more what do you want from your application perspective. So basically, what we observe is that GPU acceleration is good for scenarios that you need a high throughput. So you need like thousands of QPS. So you want to have a 10,000 or even 50,000 query per second. So that's where GPU is going to shine. You basically send a lot of data to the GPU processor for batch processing, and you get all the results in a batch.
New embeddings, especially like Colbert, Colpoly, but also Matryoshka embeddings. What challenges do the new type of embeddings actually present for vector search similarity systems, and also the new type of calculations you are actually doing with these embeddings?
So this is definitely emerging technology in the vector search space. And back in the past 5 years, 10 years, we saw a lot of application about this search. And also when we're talking about similarity, a lot of people are referring to cosine similarity. At the moment that we are in the process to supporting all these different kind of new vector search operators into our vector database. We are going to support Colbert, and we are going to support a sparse index, and we are going to also support re-ranking and customized scoring functions and things like that.
For the calculations within Colbert for the late interactions,
Right.
what kind of new indexes or what kind of optimizations to the existing ones are actually necessary to perform those efficiently at large scale?
So first of all, compared to a distance, callback is going to be more computation intensive, which will have an impact on the scale of the distributed system. So you may need a large cluster to support that. And also, like a callback also means that you are transmitting more data. So a single entry made of a higher volume of data. We are doing tons of optimization to accommodate computation and also data transmission.
Yep. And have you actually already played around with additional optimizations? Like, especially in research, there's a lot of talk, for example, about pruning, removing the less relevant tokens, for example, quantization, of course, but also caching a few of the embeddings, especially the more important ones. What are you actually considering beyond those to optimize the Kohlberg calculations?
We are exploring all these approaches, and this is still some ongoing work. And so we are not sure which approach works the best for us. Again, Milvus is a distributed system, and a lot of things going to be much more complicated in a distributed environment. And we're definitely exploring all these approaches, but we haven't decided yet.
On the sparse indices you mentioned, is this among others splayed? Because there it would be really interesting, like how are you handling the expansion at query time? Because this is always something that really bugged me about splayed, that it's really hard to implement the expansion at query time to actually make it be useful.
Yeah, so we also think this sparse index is very important because it can also it basically add another other way for us to search the data. So you can combine it with a similarity search and also dense vectors. You can achieve higher recall.
Yeah. And are there any emerging technologies or research areas that you are particularly excited about at the moment?
So there are a few technologies. So first of all, to integrate and support all this more traditional data retrieval in vector search. For example, BM25. We saw the importance to support a BM25. So to integrate a BM25 with a vector similarity search, that's one thing that we are working on. And also the other thing that we are trying to accommodate a lot of data. So when we're talking about embeddings, that a lot of people we're just talking about like text, images, but in the domain of text and the knowledge base, we found that there are a lot of data they are stored in more like a traditional, and we found out that we can actually converted all this knowledge base into graph embeddings. So there are a lot of graph embedding algorithms. So if we pick up one of these algorithm to transfer knowledge base or your graph data into embeddings, and you put this embeddings in a vector similarity search, actually you can achieve superior data accuracy. So actually, we did some experiment. We found out that you can achieve even higher accuracy on data retrieval than graph rec, for example. There are going to be more and more indexing algorithms. And for each indexing algorithm, there are a lot of parameters like segmentation size and how you clustering the data. There are tons of parameters to fine tuning that makes us to think about autonomous driving for vector indexes. And so basically we're trying to use these machine learning algorithms to provide learning on top of vector indexes. And so the customer, the user don't have to care about the configuration and the parameters of different indexing anymore, and just work out of the box. And lastly, we have a lot of advancement in indexing algorithms from HNSW to IWave PQ. But we found out that there could be like a self-learned indexes. And so it could be powered by all these AI algorithms, but it's highly customized for you data distribution. So for example, HNSW is basically a graph-based algorithms, but every single customer may have a different data workload. So what if we can use machine learning or some algorithms to customize the HNSW algorithm or the graph-based algorithm just for that data distribution, for that kind of workload. And so this will help people to achieve higher performance and also help them to achieve lower cost. And so I think those are the things that are emerging in the next few years.
Yeah. And by self-learning algorithm, or adapting index, do you actually mean that the index sees the queries and which query types are performed frequently and then basically makes those faster by adapting the index? Or is it also based on the data structure and data distributions that it reorganizes itself over time to basically organize similar items closer together?
Yeah, it could be both. So you are absolutely right. So we want to achieve both. So let me give you one example. We know that eventually you have to build several indexes. So if you have a large volume of vector data, you have to segment your data and build several indexes. And how you are going to segment your data is going to be a big challenge because you want to maintain those data locality. So if you know that the pattern that you are going to retrieve your data, you can build the indexes without sacrificing data locality. You basically have a better data locality. And also, as you mentioned, there are some data that you probably want to retrieve with a higher frequency. And then for those data, you can definitely put them somewhere in this storage hierarchy that have a higher affinity to GPU or CPU. You basically store them in the GPU memory or local memory and things like that.
Yeah, and there, like in HNSW, you have a lot of different things you could basically add on, probably like the choice of connections per node, like the number of connections per node, the number of layers you have. Like you could probably also add new entry points into the data. Are you also exploring, like in reinforcement learning custom distance functions?
So this is a very interesting idea. So we had a discussion about that, I think 1 year ago. But unfortunately, at the moment, we don't have the engineering bandwidth to explore that. But that's a very interesting idea.
Yeah, it could be really interesting. And if people really want to start building your stuff, check out Zilliz. Where can they do that? And also, what's on the horizon? What can you teaser? What should people really look out for?
I think that so at Zilliz that we have been building a vector database system for high performance, for scalability, and also without sacrifice of a cost efficiency. So for those users who want super high performance, they want a very high QPS, they want a very low latency, and also they get tons of data. They get and above, and also they want to achieve a good DCO total cost of ownership. And I think we are the solution to go.
And if people want to follow along with you, where can they do that?
So they can reach out to us in the open source community. So Milvus is open source on GitHub, and so it was one of the most popular vector database system in the world. And so just search Milvus on GitHub. And also we have a Discord channel and to hold all this discussion about vector database and about Milvus.
So what can we take away? I think there are two very different sets of learning here. One for like the developer who's working on the actual databases, and one for more of the user of the databases. So let's maybe start with the user, which is the group which I identify with more. And I think what really is obvious through the episode is how much effort you actually should spend on figuring out the requirements of the system you're building, so that you actually sit down, look at the use case, and figure out, okay, what am I optimizing for, or what do I have to optimize for based on what the user needs and also the use case requires. And this can be very different things. I think like the three main aspects I'm looking at is, for one, always cost. The second one is latency. And the last one is basically in search databases, relevance or relevancy, like how relevant or good do my search results have to be. And you have a lot of different levers to pull in your system to actually have an impact on that. So just as an example, when I'm optimizing for cost, I would place more of my data in a colder form of storage, but this also means I'm trading off the latency part. It doesn't mean I'm getting a worse relevancy, but I will have a worse latency just because of the network cost I will be encountering. And on the other hand, when I have more of an e-commerce use case where I'm in the domain of 100 milliseconds, where I have to return the results to the user, I would have to optimize for latency. So I would have to place more of the data in RAM or at the maximum in local SSD, because I wouldn't be able to basically do the round trips in the network before I have to return the results, especially when I have to move large amounts of data, which I have to in search systems. And the last one is the relevancy. And here this could mean when I have a use case where relevancy is of the utmost importance. And this could also mean that like latency doesn't matter at all. So when I'm looking, for example, at report generation, which is something that is typically done more async, so the day prior, the night prior, and then it's served to the user, I really can take my time and can focus more on getting a really high relevance. So doing, for example, an exhaustive search over the entire vector database, because I just don't really care about the latency I will have. The other thing would be I could even add more components. So for example, a re-ranker, which is something very hard to do when you're actually working in a low latency environment. And I could also, when I have a use case where I actually need high relevance, but also very low latency, then I would have to trade off the cost massively and probably go into GPU acceleration or just adding more nodes to handle all those QPS. And I think being explicit about this in the very beginning, what are you optimizing for, is what will get you the good results when you're actually building the system down the road. And the other set of learnings, which is more of the like database engineer, or however you want to call it, who is building the databases, is there are a lot of different like interesting things they've built that have emerged over the years of building databases. Like one, the dual path of search, like you have a write path which is going to a buffer and is only indexed once you hit a certain threshold of data. And the read path basically queries from the buffer, but also the already indexed data. And I think that's very similar to Cassandra's LSM tree. And also like it looks a lot like a cache aside. And you can basically achieve the real-time searchability. So basically the data is fresh without really sacrificing the performance, because you couldn't search it in real time if you would have to build the index first. And also the hierarchical storage element, like having, for one, like the fastest is the GPU memory, then you have the RAM, then you have the local SSD, and then you have the object storage. And in each one of those, you have a different bottleneck. So in GPU memory, the bottleneck is CPU to GPU transfer. In RAM, the bottleneck is memory bandwidth. In local SSD, you have I/O operations. In object store, like S3, you have the network latency. So you have to solve a lot of problems to actually make this work, but you basically can do a refined search and go basically through the different types of data. And he also mentioned that they have different amounts of data tend to be stored on the different types of storage. So for example, the GPU has 1% at the maximum, probably even less. And the in RAM are 10%. Then in disk and object store, I think this is where at the moment the main trade-off is done, like on the local SSD or whether it's in object storage. And the ratio, I think, was really interesting. I think he even mentioned like 89% is roughly on local SSD. And the architecture basically allows them to maintain the high performance while still handling massive data sets in a cost-efficient way. And this is again going into like the trade-off direction, like what are you trading off for? And as a systems engineer, database engineer, you basically have to build the wheels so the user is actually able to make his decisions on what he's optimizing for. But yeah, I think this was a very interesting episode. We will be going even deeper into Milvus and its architecture in an upcoming episode. I'm not sure whether I will post it next week or at a point later in this season. But to stay up to date and to catch the next episode, subscribe. Also, let me know what you think. Post it in the comments, whether you're on YouTube or just send me a message on LinkedIn, Twitter, Bluesky, wherever. And yeah, I will talk to you soon. Have a good one.